This is part 2 of the Chapter 2 Slide Set A recordings, and we are on, it's either, I think it's slide 31, 30 or 31 or 32, somewhere around there. But we're looking at the three basic types of mixtures. You can have a solution, a colloid, or a suspension. And a solution is just, for example, salt water. If you have a solution of salt water, it's going to be like completely, light can pass all the way through it. It's completely like transparent, I guess you say. If it's a colloid like Jello, and a better example of a colloid, let's see, what would a colloid be? I think like you could say the cytoplasm in our cells, I'm pretty sure, is a colloid. Another example of a colloid is some people like whipped cream or Cool Whip, and that is an example of a colloid. But that is when the solute particles are larger than they are in a solution and they scatter light. So you can't really see, it's not clear like a solution is. It's not clear all the way through. In a solution, you wouldn't be able to see like that there were any particles dissolved in there. But in a colloid, you would. So Jello is an example, and I'm pretty sure that the material, the fluid that makes up the inside of our cells, which we call cytoplasm or cytosol, is a colloid. And then a suspension is when the solute particles are very large and they can settle out. So blood is a good example of a suspension. Blood cells are suspended in plasma, but you can take a sample of blood and spin it in a centrifuge, and the heavier particles will settle, kind of like, Italian salad dressing. You can shake it up and it'll mix evenly, but then as soon as you set it down, the heavier stuff is going to settle to the bottom and the oil is going to rise to the top. So plasma is going to rise and the blood cells are going to settle to the bottom in a sample of blood. So that is a suspension. It's when really there's nothing dissolved in the first place. It's just mixed up really good. And as soon as you set it down, the heavy particles are going to settle out of the solution. So you've got a solution, a colloid, a suspension. And definition of solution is that it's a homogeneous mixture. And we talk about solutions a lot more in biology and A&P. The solvent is almost always water. And then the solute is whatever is dissolved in the water. So, for example, blood sugar is dissolved in the water in our blood plasma. So the blood plasma, which is mainly water, is the solvent, and glucose is the solute. When we talk about the concentration of solutions, we typically say we're using terms that tell us the amount of solute dissolved in the total amount of solution. So sometimes we'll use a percent, and in fact, most of the time we will use a percent. Salt solution is 10%. Then that means 10% of that solution is salt and 90% is water. We use blood glucose levels a lot, and we don't always know what they mean. Normal blood glucose is between 80 and 120 after 2 hours of eating. Normal fasting blood glucose, we want that to be lower than 100. I happen to know because I am a diabetic, and my daughter is a type 1 diabetic. I have type 2, but we are both she's had it since she was 2 years old. So we're both very well educated on blood glucose levels. So 80, if I could get my fasting blood glucose to 80, I would just be so happy, but I haven't in many, many years. It's been above 100. But what that 80 means, let's say you check your blood sugar, you check your, you prick your finger and you check your sugar with a glucose meter and it reads 80. That means 80 milligrams of glucose in 1 deciliter of blood plasma. And we don't use measurements like that much, but that tells us the milligrams of glucose in 1 deciliter, which is 1/100th of a liter. And that's what those units actually mean for blood glucose. Now, we're never going to use this, so I'm going to skip it. We're not going to do molarity in biology class. That's for chemistry. And then this page just, okay, I was right, good. I'm glad I didn't tell you anything wrong. I might do that sometimes. I try not to. But cytosol or cytoplasm is a colloid. And then suspension is blood. I'll highlight that. So an example of a suspension is blood. All right, so those are the 3 types of mixtures. Now we're going to go on and talk about chemical bonds, which are attractions between atoms. They're not actually physically held together. They're just strongly attracted to one another. And chemical bonds are determined by the number of valence shell electrons. Now, in chemistry class, you would have to do something called, if I can remember, electron configurations. You would have to be able to tell how many electrons are in each electron shell outside of the nucleus of the atom. In this class, you don't. You just need to understand that the outermost electrons, the ones in the valence shell, which is the outermost electron shell, those are the ones that participate in chemical bonds. So to understand how ionic bonds and covalent bonds form, we have to understand something called the octet rule, or the rule of 8s. And that is that atoms desire 8 electrons in their valence shell. In other words, when they don't have 8 electrons in their valence shell, they are unstable and they tend to react, like explode or, form chemical reactions. So atoms are always seeking to fill their valence shell with 8 electrons. However, they can do that. So the octet rule says that atoms desire 8 valence electrons, is how you would say that. There is an exception, and that would be for hydrogen and helium. They are stable with only 2. Their valence shell is stable with only 2 because they are so small. So almost every other atom is going to seek to have 8 electrons in its valence shell. Most atoms, the only ones that do have 8 electrons are what we call the noble gases, like helium, which has 2, and then there's neon, argon, there's different ones, but they have got 8 valence electrons, and that's the reason they don't form chemical bonds. But most atoms are either going to gain, lose, or share electrons in order to become stable and have 8 electrons in their valence shell. This is showing you 2 atoms that are already stable. Helium has 2, and its valence shell is the first shell, so it only needs 2 to be stable. But any atom, which is almost all the other types of atoms, their valence shell is going to be the second shell or higher, and it needs 8 to be stable. And you can see neon here has got 8 valence electrons, and it is stable. So neither one of these 2 will form chemical bonds, and we call them noble gases. But then you look at carbon. Carbon only has 4, so it is not stable. It's unstable. Sodium only has 1 valence electron. It's unstable. Hydrogen only has 1, and oxygen has 6. So all of these are examples of elements that are chemically reactive. So let's talk about ionic bonds first. An ion is an atom that has gained or lost electrons. And if it gains or loses electrons, it takes on a charge, an overall charge. Electrons are negative, so if an atom gains an electron, it takes on an extra negative charge. if it loses an electron, it has an overall positive charge. So we call it an anion if it gains an electron and has a negative charge. We call it a cation if it loses an electron and has a positive charge. So ions have a charge because they gain or lose electrons. You've probably seen this example before. The sodium has 1 valence electron and the chlorine has 7. Let's highlight those 7 so you can see. So the sodium, I didn't mean to do that. Let's see if I can erase it. Sorry. Erase. Eraser. Just that part. Okay, so you see them here. I apologize, y'all. I just hate for it to stay that way. Okay, try one more time. Don't go so fast. All right, and then these two. All right, so the chlorine has 7 valence electrons. The sodium has 1. If sodium will lose that 1 and give it to chlorine, chlorine will now have 8. And then, since sodium loses that 1 valence electron, its valence electrons are now the ones in the second electron shell. So sodium will also have 8 valence electrons if it loses this 1. And you can see that here. When sodium gives an electron to chlorine and the chlorine takes, that electron is transferred to the chlorine, then the sodium has lost an electron and takes on a positive charge. The chlorine has gained an electron, it takes on a negative charge, and opposites attract. So the opposite sodium cation and the chloride anion, those opposite charges are attracted to one another and they form sodium chloride or salt. And that's actually table salt. Other ionic compounds are also called salts, but sodium chloride is the only one that we call table salt. Then we have covalent bonds. And covalent bonds form not by losing and gaining, but by sharing electrons. And we can have 2 types. They can be polar or nonpolar, but we'll get to that. This is a covalent bond. It's 4 covalent bonds, actually, that form between a carbon atom and 4 different hydrogen atoms. So each hydrogen needs 1 more electron to have a filled valence electrons of 2. And the carbon needs 4 total. So if each hydrogen shares its 1 with carbon, and then carbon shares 1 of its 4 valence electrons with each one of these hydrogens, here's what we get. We get hydrogen has 2. Each hydrogen has 2. Here, 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 and here. And then the carbon has a total of 8 now. So by sharing or forming a single covalent bond with each of the hydrogen atoms, the hydrogen is stable and the carbon is stable. We can look here at a molecule of oxygen gas. Each oxygen has 6 valence electrons. So if it shares 2 with the other oxygen atom, that gives each oxygen atom now 8. So we'll just look at the oxygen atom on the left and count the valence electrons. 1, 2, 3, and then these 4, goodness, would be 8. 1, 2, 3, 4, 5, 6, 7, 8. So the oxygen on the left has 8, and if you do the same thing for the oxygen on the right, it has 8 too. And nitrogen can do the same thing, except it's going to form a triple bond because it will share, each nitrogen atom will share each nitrogen atom will share 3 electrons with the other one. So that's going to form a triple covalent bond. Now, the ones we just looked at are called nonpolar covalent bonds because the electrons that they share are shared equally. But we also have, and carbon dioxide is also a nonpolar. So the oxygen atoms and the carbon atom share their electrons equally among each other. There's not an unequal sharing. But when we have polar covalent bonds, like we do with water, that means the atoms that share the electrons share them unequally. So there's going to be a partially positive charged end of the molecule and a partially negative charged end. Let's just look at water so we can see. All right, so in water, the hydrogen atoms and the oxygen atom share a pair of electrons. Okay, so here's the shared electrons. This is 2 electrons being shared between hydrogen and oxygen, and then 2 electrons being shared with that second hydrogen. But what happens is the oxygen atom is larger and it has a stronger pull or stronger hold on those electrons. We say that the oxygen atom is electronegative. It's more electronegative than what the hydrogen atoms are. So the hydrogen atoms will have a slightly positive charge since they don't have as strong of a hold on those electrons. And what that does is it gives the molecule 2 oppositely charged ends, negative and positive, and that makes it a polar molecule. And because it's a polar molecule, then it can form, water can form hydrogen bonds. And what that means is that, and there is a video, and this is actually, I can't show it on the slideshow, on the recording, but you can watch it. It's on slide 63. You can watch hydrogen bonding. And I just encourage you to do that because I think we're really toward the end. We need to cover chemical reactions. Okay, I'll make another one. I'll do another recording. All right, but you on your own go back to the PowerPoint slides in the Moodle. It will be week 2 in your week 2 Moodle course. Go back to the PowerPoint slides and go to slide number 63 of Chapter 2, Part A. There's 2 sets of slides, 2A and 2B. Go to 2A, and it's number 63, and watch the animation on hydrogen bonding.